Good day to you. This is Anagalactic bringing you the second part in our series on null un dual. Correctly translated, that would be 0, 1, 2, the most important numbers in all of mathematics. We were attempting to get at 0 because it turns out that is the mathematical equivalent of Euclidean null, which is 0D. This point, as it's called, occupies the center of any linear system all the way from 1D to 4D, and there are higher constructs, although they become quite infamously complex and virtually worthless. We are currently constrained to 4 linear dimensions by spacetime. Again, there have been penetrations. I used to use a geometry, which you can use also, which is a 5D system called conformal geometric algebra. We won't be covering that today because, again, it's linear mathematics, which we are going to transcend now. This presentation is my latest effort at providing the entire proof sequence for what I discovered in geometry 3 years ago. In this presentation, we'll begin where we left off at the number 2. But a quick recap, especially if you haven't seen the prior video from earlier today, the 7th of May. I'll recap what is in that video, which is actually currently uploading, so I know you haven't seen it. You won't see this first, though, unless you go out of order. But they are meant to be together. The reason I mention that is the prior video is unusually long. Even for me, it's 2 hours long, although I believe it's an excellent video, and I do encourage you to at least scan or skim it before watching this. But I like to keep all of my videos as self-contained as possible. So what I mention now will be rather hasty, that is cursory. In order to give the recap, I will be condensing a lot of information. The numbers 0, 1, and 2 do appear to be in sequence, and in linear space they are indeed in sequence. 0 turns out to be an unusual number for several reasons, but I think we all know, to some extent, that it is a unique number in the linear system. It does comprise a geometric object which Euclid axiomatized in the first sentence of Elements. Now over here you'll see one of my favorite portraits. It's a very simple portrait, a photograph of the lunar surface at about the phase we call half moon, sometimes called a quarter for reasons which have historical justification, but you can see that that is half, approximately, of the lunar surface. Now, the moon itself, if seen, for instance, from above, always looks like it's half, because it is half. But because of the angle of the incident sunlight, it does change phase from new moon to full moon and back to new moon again on a continuous cycle. The reason I enjoy this photograph so much is because it's the very first lesson that every human, without exception, gets, and it's not from a teacher, unless you consider the universe to either be a teacher or to be equipped by a teacher to give the message from a teacher. But it does teach us geometry, and it's a critical geometry. It serves us for the rest of our lives. Now, what a person does with knowledge that they get, even directly from the universe, is a matter of human development. There's quite a few vicissitudes for any human, depending on where and when you were born, and indeed how long you live. But the reason I introduce our topic today with the photograph of the moon that you see is because there are two circles on it at all times, and those circles are at right angles. I find this the most fascinating topic. The first circle is simply the perimeter. If this were indeed a disk, which you know it's not, it's a sphere, but it looks like a disk to us, and that's actually how we see. We do see the disk. You can already convince yourself that you are seeing a flat screen image and not a sphere. We don't see spherically in the same way that our brains, our minds, pick up the image. It's actually flat screen. And that's been proved by physiologists. That's why a flat screen image looks so real. It's exactly how you see. So you can't tell the difference. That's superpositional, though. You actually could tell the difference, and we actually do train ourselves to tell the difference. We all know that that's a sphere. And there's a way you can convince yourself of that, although it is possible to be fooled by a very good optical illusionist who composes what is not a sphere so that it looks like one. Max Escher's paintings, I should say his tilings, give us the illusion of a hyperbolic surface, which is quite fascinating. It certainly was to Sir Roger Penrose, who befriended Max Escher, and they became rather good pals and exchanged quite a bit of information. Sir Roger talks about Escher a lot. They did meet. Now, one of the circles, therefore, is the perfect circle of the moon. The first footnote that anyone would bring up if they're not thinking the way I am would be to say, no, that's not a perfect surface. It's not a perfect circle. There are craters that stick up even at the edge, and you can see that in this image. But I'm speaking of the virtual circularity. It's obviously not going to be even at the edges. But it's still a perfect circle, and that's reasonable to say with that footnote. There's no contradiction. It's because of gravity, as we know. The moon was formed into a sphere by, you would say, a natural process that involves gravity, because there's a center to gravity, and that's why the Earth is spherical, and indeed, much more significantly for a proof, that's why the sun is spherical, because the sun is not made of solid material. Technically, it's plasma, which is ionized matter. So it is mostly hydrogen, but it's in an ionic state, which is basically to say that it's on fire. It's very hot. So we get a lot of sunlight that way. But it is essentially a spherical surface. It's a gravitational spherical surface. And then the sun itself is neither, as the moon, it's neither of them are perfect spheres. They could not be. It's physically impossible. But in geometry, we know what we're looking at. That's not a triangle. That's not a square. That's not an ellipse. It's a circle. And so the moon is a sphere. And that's quite significant. We're going to talk about that today because where we left off in the prior video was with the introduction of the number 2. So we're just going to recount what we learned about 0 and 1. 0 is not a number, although it's superpositional for the linear systematic space, beginning with the line itself. 0 is necessary to create the metric for distance, because you have to cut off the line and call it 0 in order to have a starting point for your distance measurement. So we all know that. The number 1 is the first counting number, and it has some special properties that we discussed. Most significantly, we want to compare 0 and 1 because they share a most amazing property. 0 is extraordinarily peculiar. It is unique in linear space. It is the center of a line that is the diameter of a circle. So you can say that there is a 0 at the center of any circle. However, that line can be oriented in any direction on what we call a 360-degree circle. That is, you can rotate the line, and it's still the diameter, it doesn't change. So we're going to capitalize on that fact, but what I'm driving at is that 0 has a mathematical quality called identity. And whenever you say identity number, you must refer to which operator, because there are two identity numbers, and only two, in the basic linear number system, which begins at 1 and proceeds as high as you like. So there is an infinity involved, but we just simply disregard that and use a finite section of the line for distance. This makes the starting point mathematically unique because 0 is not a distance by itself. In fact, it has no properties by itself, and that's how Euclid axiomatized the point. It has no dimensionality, which, if you wanted to get philosophical about it, you could suggest that it doesn't even exist. It does, though, by a retroactive definition that makes perfect, coherent sense. You can say that that 0 is a position in space. So that's the nature of 0, that it is a position in space that's represented by a very special linear number called 0. So that takes care of 0. We were able to go forward a little bit, and we're going to go forward again with that, to discuss the nature of the BH, as I've abbreviated it, but you don't know my coding system, so it's supermassive black hole, which I like to abbreviate because it's such a mouthful and it's also misleading. So what is called the supermassive black hole is considered to have a geometry that is considered to have been discovered and verified. And the geometry of the SMBH is that it would have to have a center. But computing the gravitational potential, that is, the actual gravity of the object, the center is a runaway infinity, which is redundant. It's essentially an infinity because it's impossible to describe that density. It's actually a characteristic of the density of the object, that it's very compact considering how much g-force it creates from itself. So what makes that happen? We'll get to that. Science hasn't gotten that far. Science is not certain about how the black hole forms, although of course there are theories for everything. But it does have a center called a singularity, which was quite a hot topic for a while, and it's subsided because now it's accepted that the BH has a very special center where 0 becomes a problem. And we'll get into that today so it doesn't sound like some kind of word puzzle or math puzzle that only a brainiac could figure out. It's actually quite simple once you know the correct geometry, which your physicists, by the way, have not discovered. So there's a great deal of misinformation about BH. We're getting to that, but for now, I'd like to turn this off. And now I'd like to turn something else on. Now that, you will see, looks like there's a line coming out of a center. This is not considered to be a BH. This has another name, actually several names depending on whose system you're referring to. This is mostly an historical artifact, that this has changed names. This is a class object called a quasar. And it's a special quasar, although it's a kind of quasar, which is the brightest thing in the universe. It's essentially, you could think of it as a galactic scale star, but it's not stellar. It's quite a bit different. You can see that it does have a bright center, and that is typical of this kind of object. That is extremely bright. We won't say exactly how extremely bright because it's not pertinent to what we're doing. I'm just going to expand this just a little so you can see both lobes. This also has another name, a dragon, without an O. It's DRAGN. And for those of you who study astronomy, you may recognize the AGN in DRAGN. AGN stands for a galactic nucleus. It's called an active galactic nucleus, basically because of that bright light. Our own galaxy, and in fact most spiral galaxies, virtually all spiral galaxies lack this center. It's more typical of an elliptical galaxy, which tends to get brighter and brighter toward the center because there's more of a concentration of stars, but it's still stellar light. But this is essentially a kind of galaxy that's forming. And we'll get to whether it's going to be a spiral or an elliptical, which are quite different geometrically. They have one thing in common, though. They do have a center, which is considered to be a gravitational center by astrophysicists. Our own galaxy has an SMBH. It's a small-scale SMBH. I believe it's on the order of 100 times less dense, that is, really less matter, than M87, which is not very far from us and was the subject of a photographic effort to photograph the center of M87 to see if we could actually photograph where the black hole would be. And that was touted to have been done. There's a certain amount of controversy surrounding that photograph and the claims made of it. I would put it this way, that where the BH is considered to be in M87, which of course is at the center, was photographed. But this is quite different, and an AGN always has this bright center. M87 does not have this kind of a center, called an active galactic nucleus, which is abbreviated AGN. Now in Dragon, that's simply to add 2 more letters to the beginning. It's kind of catchy, I guess. It's a double radiolobed. And you can see the 2 radiolobes. The reason they're called radiolobes is that radiotelescopy had to be developed first in order to see these lobes. You can see they're colored blue here. That's to show that it's in the X-ray. Radio. That's why they're called radio lobes. The scale here is kiloparsecs, thousands of light years. So this is galactic scale plumes. They're 2 plumes. And the reason I'm showing this to you is because this has an enormous amount of relevance to the topic of the BH. The BH is one kind of center of a galaxy. This is the other kind of center of a galaxy, where instead of having a super gravitational object, as the BH is considered to be, this is a super luminous object. Super luminous, extremely bright. And we'll get into just how bright that is. But the plumes you can see are coming out on a straight line. And it's a bipolar line. It would have to be because those jets have matter in them, material. And it's coming out at what is called subluminal speed, which is a very high fraction of light speed. But it's not light speed. But since it's a velocity, it has to be compensated according to Newton. For every action, there's an equal and opposite reaction. What you're seeing is very strongly related to an electromagnetic system. Anytime you have very fast moving electrons, And that's partially what this is. You have a magnetic field. The two flows of what might be characterized as electricity going out, it is an electric phenomenon that is known but not understood. And therefore, according to Maxwell and everything we know about electrodynamics, there is a huge magnetic field associated with those two jets. They're called jets. And what is coming out is not understood at all. Not really. But I would like to point out to you, just so you have a little more information to work with, first of all, those plumes are thousands of kiloparsecs long. And you can see that it comes out quickly from the center in very narrowly collimated beams, which are straight, they're linear. But when it reaches a certain distance from its origin, it's actually slowing down and expanding because it's encountering some medium that's slowing it down. And then at the extremes, you'll notice on this diagonal here, they're plumes, they're actually clouds. And the upper left one is turning. This whole thing is rotating, and that plume is coming toward us, and that's why it's brighter. The lower right-hand plume is spinning away from us. So this is spinning. Now, what we just saw is quite a bit different from the moon, where there are no straight lines. There's no straight line anything. There's no straight line geometry in that shot of the moon. But in the shot we just saw, there is a dead straight line, and it comes out of a center that is a geometric center that can be computed, obviously, because both collimated jets going in 180-degree opposite direction, although there's a footnote there, it is spinning. So one would have to ask, why are these jets of material coming out? Why are they going so fast? And why is it spinning? This is a direct line of solution for the supermassive black hole mystery. I want to turn that back on so you can see this as I'm talking. It's obvious that those two jets are being generated from the object itself. Are they coming from inside? Yes, they are coming from inside. How far inside? Because if it comes all the way from zero, it's coming from another dimension. It's coming out from a null point. Well, we know that that's physically impossible. And so there has to be another explanation. The gravitational balance is at the center. And since this is mass, it does have a gravitational center. Well, then those two beams are defying gravity. So there's a force behind these jets, collimated beams of material. It slows down, turns into a cloud, and spins. It looks like it's the beginning of a spiral galaxy. It may be just that. We'll go on to discuss that, but what I want you to see is the center. That is so bright that literally words can't describe it. It's so bright we can't even say how bright it is. It's so much brighter than starlight that there's no comparison. However, we have taken spectrograms of these objects. Hundreds of these objects have been photographed. You won't find them out on the internet. You used to be able to find them, a lot of them. But the furor has died down. And if you were to study these objects further on your own, you'd end up learning the truth about what they really are. And that's verboten now. You are required to stay confused. you're required to listen to what the universitarians, that is, the mathematical physicists, say. You're not allowed to disagree with them, and that's enforced now. I'm here to defy that because it's meaningless to a wise man. I'm not restricted from giving you the truth of what that thing is. But you may already know that there's an extraordinarily well-developed theory that partially would explain how these jets are formed. You may have heard of it. It's called an accretion disk, which means that those jets are not coming from the center of that bright light. It means that that bright light has a amount of matter around it that it's not part of the object itself, but it's spinning so rapidly that it's being thrust into two collimated jets. That theory makes utterly no sense. It's a total kludge. It was manufactured so as to avoid the truth. That object that you're looking at is one of the most magnificent, fascinating, instructive objects in the universe, and certainly for us as amateur physicists, we definitely want to know what that is. Why are those two jets coming out? Now, what I wanted to show you is that's a straight line coming out, and it's a bipolar line, so it's just like Euclid's line, and the center is 0, and the numbers go out. Now, in this case, it's distance in both directions. So there's no such thing as a negative half of the line. They're both positive. And that's where the similarity with the line kind of diverges from how we use our numbers on the line, as positive and negative. The universe doesn't use negative numbers. They don't exist. That's a fact that you'll accept. You're going to see it in this lecture. I'm going to prove that. There's no such thing as negative numbers. Even for subtraction, so-called the inverse operator of addition, that operator, it does not exist. There's only addition. And the reason I can say that is that subtraction is meaningless. Even if you insist that there are negative numbers, you don't need subtraction at any time. Addition will take care of any situation for linear numbers, that is, integers. Addition is the only operator. However, there is a geometric opposite, and that's where we get the negative numbers from, and the negative numbers are useful. It is superpositional. I say exaggeratedly there's no such thing as negative numbers. That's only relative. Obviously, we use negative numbers, and they are also used geometrically, certainly in the construction of the complex numbers, which is quite profound, and we're going to get into that as well. We're approaching the number 2. How many jets do you see there? There are 2. Now, the way we introduced the number 2 was in the wavelength-frequency relationship, where rather mind-stretchingly we can say that there is a lowest frequency. It is 2. No such frequency has ever been discovered because, of course, if it has a frequency of 2, what's its wavelength? Well, it's 1/2. But then 1/2 of what? The way we measure light is by frequency, but we can also measure it equivalently on wavelength. Those are two coordinated numbers. And so, for instance, if the wavelength, for instance, in nanometers, if you pronounce it that way, you could say that a certain color has a certain number of nanometers, which is measuring what? Its wavelength. Frequency is not a length, but it's always involved with that wavelength. Is wavelength a length? Yes, but it's not a linear length. It's a length around a circle. And that's called wavelength. Very poorly understood, and frequency is almost entirely not understood. The reason is it's not in space. A frequency, even the way we use the word frequency, has to do with click, click. That's the frequency, and it has to do with time. In this case, it has to do with energy, and the frequency is the measure of the energy of the photon. Nobody disputes that. Frequency is energy, and you should say it two ways so that you grasp the geometry of it. What you're looking at is linear, but you would have to say it's only linear in the sense that it's not a curved surface. There's no surface. The center does have a surface. It has a radius. Now, to say what is the radius is quite a challenge for this object as well as for BH. The radius of BH is an extremely controversial and difficult topic. We're going to break through all of that rigmarole so you'll see what the object actually is. It's not nearly as complicated as your physicists have made it. So that you're looking at is not BH. BH does not have these plumes. However, you can see that they're very closely related. The big difference, as we all are aware of, is that BH has no light. It does not emit light. There's a footnote to that as well. Due to the research of Hawkins, Stephen Hawkins, and indeed Sir Roger Penrose also, you would have been able to say Sir Stephen Hawking, except Sir Stephen turned it down. He didn't want to be called Sir, so he just refused it. And so did John Lennon, by the way, if I'm not mistaken. So this is related to BH, which has a singularity at the center, a mathematical object which we identified as the null point, which is the reference frame for a gravitational field. Every gravitational field, including that of the Earth, or any object in the solar system, or anything we've discovered at macroscale, has a gravitational center. And so does a BH. It has a supposed gravitational center. It has not been proved yet that that's gravity at all, because nobody knows what it's made of. The best guess, of course, is gravity, and that's accepted, but it's not law. It's part of a theory. There would have to be corroborative evidence besides what we've already discovered, which is quite confirmatory of what we would think of as gravity. But I want you to keep an open mind on that, because there's another aspect to the phenomenon which is critical to see, or you'll end up just as stupid and uninformed as your astrophysicists who have no clue what these objects are. No clue whatsoever. They've just made up stories that seem plausible to them. We're going to blow all that apart so that you actually see what these things really are. It's much, much more profound. It's even science fiction-like. The truth, it has been said, is always stranger than the fiction. In this case, definitely so. You're being taken to the cleaners. You're being robbed of understanding by men who are after nothing except money. Nothing except money. They've been bred to do so, and most of them are completely unaware of it, I would have to assume. Otherwise, they'd realize they need to get with the program. Your astrophysicists are goners. They'll never understand anything. They're done. They're liars. They are deceivers. And I impugn them all, every last one of them, and I will stand up to them and debate any man on what they think they need to correct me about. Nobody's going to correct me ever. Not now. I've got the answers. I know what these things are. So we're also going to get into the quantum mechanical situation, because you'll see that these are related. It all has to do with that number 0. It's just so remarkable to be able to say that, partially because nobody's been able to find the way out. We're going to find the way out now. So, where we left off, we got the 0, that's the singularity, at the center of BB and BH. 1 is the multiplicative identity. And we found out from the wavelength-frequency relationship that light has the value of 1. Max Planck discovered that, and nobody doubts it at all. It's because the wavelength and frequency always multiply to 1. And as I was saying, if you're considering a frequency in the visible spectrum, you will hear it said that blue, for instance, is about 400, well, it's about 540, what? 540 is measuring the wavelength, not the frequency. The frequency is the multiplicative inverse of the wavelength, a remarkably simple mathematical fact that for all light, at any frequency, at any wavelength, all light has a value of 1 if you multiply the two component numbers together. If you multiply 2 over 1 times 1 over 2, it always comes out to 1. The name for that relationship is the reciprocal relationship, which is strictly a mathematical term. Now we're going to get into the heart of the matter. There's also a geometric name for that relationship. Now on the line, there is a geometric relationship, you certainly could say so, of 180-degree valence. That's why negative numbers are the opposite of positive numbers. Because on a line, as you leave 0, you could say that going in this direction is negative, whereas going in this direction is positive. That certainly has worked for us for about 2,000 years, so it would be a little hazardous to impugn that insight, but you see it's an incomplete insight. It's a suggestive insight. It served us so well we haven't managed to look beyond it. But that is polaric. And that forms the basis of electromagnetic charge. That the actual numbers are opposite. We won't get into electrodynamics right yet, but we are approaching that topic as well. We're going to have the unified field solution in just a moment. In order to get it, though, the hard part is to decide what in the world went wrong. Why are our astrophysicists literally stark raving mad? Why are they crazy? It's because of the number system they're forced to use, which they don't believe they can escape. And that does have the singularity built right in. Albert Einstein fell into the same trap. Einstein, I can't say he got lucky, but he definitely found something that was hard to find, which is the relationship between time and space such that you could say that they're orthogonal. And he did say that, and then he proved it. And I've shown in several of my presentations why that's true. It is a linear solution for a spherical problem. So he did get lucky, in some sense, that he intuited and then was able to prove. He was correct. Time is perpendicular to space, for the same reason that magnetism is perpendicular to electricity. They are perpendicular. Maxwell said that and proved it. They're perpendicular. And those of you who know electrodynamics are ho-hum, of course it is. But do you realize how profound that is? It's not polar opposite, it's right angle. And that leads us to our conception of two as duality. That two is an adjective, or you could say it's a noun. In the same way that one is a noun, if you say that it's unity, that is correct. One is unity. That's what one means. 0 means nullity. Nullity, which is a very interesting concept. That's actually an infinity. It certainly is imaginary. And those two are related, as I'll show you shortly. So there's a lot of synthesis ahead. The nature of gravity is that it's non-linear. Gravity is non-linear, right? That's true. What about light? That also is non-linear. So what are they if they're not linear? They're spherical. The spherical nature, that is the Spherical wavefront or spherical waveform of light has been known about for 3 centuries. Light is peculiar because Einstein did show that at certain specific moments it's a particle. And from that you could extrapolate and say that the photon is a particle without specifying it's only at absorption or emission that it's a particle, or that it appears to be a particle. We'll get into that because that's the solution to the quantum paradox, which I will divulge to you in this presentation. But in order to get at that, we need to reparameterize planar space. And that's why the title of this second video is Planar Space. Now, what is planar space? We started to get into that. It's not one. It's not 1D. It's not one-dimensional. It's two-dimensional. But you have to be more specific. It's two linear dimensional, because those dimensions are a line this way and an orthogonal line this way, and that parameterizes the space that we call the plane, but there is a price tag that's quite hefty. You're squaring the plane. Now it's nothing but squares, and that's why squared numbers appear everywhere in physics, including c squared. E equals mc squared. Well, why is c squared? Because you have no choice with linear numbers. If you want to raise that to another dimension, it's going to be 2D, and that's a square, if it's equivalent in the xy directions for the plane. This is not for volume space. When you switch to 3D and you get volume space, you still use the Pythagorean theorem to get distance, and you're still making squares, except now the squares are cubes. So 3D space, whenever you say 3D, you're saying ice cube space, ice cubes. I'm adding the word ice to make fun of it, because it's a serious mistake to do that. Well, nobody's ever realized that. And also, it's too much to say that it's a mistake. Linear systematic space, linear systematic geometry, and linear systematic mathematics is coherent if you obey some rules. For instance, you cannot divide by zero. You never can divide by zero. Also, if you multiply by zero, you lose information. That's very rarely taught. So zero is a serious problem, but not for add. Add requires zero because it's the additive identity. And I'm going to teach you a very powerful word now, which comes from Archimedes. So this is an ancient introduction to calculus, which we're going to penetrate. We're going to solve the calculus so that it's not any longer necessary. It is necessary to somehow get rid of calculus, because calculus is a huge error. Just to use it at all, it's incorrect to use calculus. If you're trying to compute reality, which we are now, we're not trying to make rockets, we're not trying to engineer to specs. And that's what you use calculus for. It's to cheat. We can't cheat anymore. We're looking at reality. So when you go to 4D, you're sunk, because now you have a structured nullity at the center, and that produces all kinds of hideous and psychotic problems, which is why your astrophysicists are stark raving mad, and it's nothing short of that. They're out of their minds and they don't know it. A terrifying situation for people, just ordinary people, such as myself or yourself. That system of lies has to be dissolved. I discovered the way to do it, and it's the only way to do it, and it also rather lets these suckers off the hook because they simply couldn't see what I see. Now, gravity is spherical, not linear, and light propagation is spherical, not linear. You will accept those statements because they're irrefutable. They've already been decided, in this case correctly. So that's not a dream image. So we're not any longer dealing with linear grid space. By the way, those cubes, or in space-time, hypercubes, are, they have hard right angles at all the positions, obviously. So that you already know that the system is wrong. That form of geometry, which is the only form of geometry known to man until me, is called extrinsic. And I'm rather certain that you've never heard that term, extrinsic. Well, that implies that there might be such a thing as intrinsic geometry. If you look that up, you'll be directed to several sites, including Wikipedia, which talks about intrinsic geometry, but this is a tragic, tragic thing I have to report to you. So I certainly hope you believe me, because what I'm about to say is extraordinarily unpleasant. If you look up intrinsic geometry, you'll get a pack of lies. Very similarly, if you look up non-Euclidean geometry, there's no such thing. It's said that Lobachevsky discovered it's not non-Euclidean. And there are two versions of non-Euclidean geometry, both based not on denying Euclid at all. It's all Euclidean. Why would they say non-Euclidean? Because it's the first time anybody ever defied the parallel postulate. Well, that's not Euclidean geometry. Euclidean geometry is the first two sentences of Euclid, the definition of the point and the definition of the line. The rest is meaningless to us. We're looking for the basis of geometric numbers. And we've only had one, geometry, because we must use single component numbers. Those are linear numbers, just one number at a time. What we want for the plane is a two-component number. Broadly speaking, similar to the complex number plane. Well, how would we do that? You have to have linear numbers. So it does seem that you would have to have a line. Indeed, you do. But there's a trick that nobody noticed. Not Archimedes, not Einstein, not anybody. I'm the first person to have seen one of the most amazing tricks. And it looks like a trick, but it's actually quite sound and coherent. So let me go into this. This is the first time I've presented this attack venue in this particular way, because there's several ways of approaching this coherently, consistently, and completely. To reparameterize the plane so it's not squared. So it is not squared. So it's not squared. That's a bad joke because I have allergies. Let's not go there. So is that possible? It doesn't seem possible because you have to begin with a line to have numbers at all. So we're going to do so. We're going to do what Euclid did. You start with a point, which is simply a position. And then you make the line, and you're done. Now, what can you say about that? The line hits two infinities. And you can prove that the center that you started from is the center of those two rays. So this line that we talk about so often, just in pure space, just without any bells or whistles, there's nothing except this line. You can prove that it has a center because it has two edges. Now, the trick is to see that when you draw the line, even in your mind, it's in some space. You're drawing it on some blackboard. That's spheric space, and I proved that in 2022 because these two rays do not hit two infinities. And you'll realize that when you realize that that line, no matter how big it is the diameter of a sphere. We're going to start with a circle because this is the way nature designed us to see this first. And by the way, nature also designed that we would study Euclidean geometry. Well, 2,500 years seems like a long time, but it depends on how you feel about it. It's more of a subjective reaction. But it did take 2,500 years to realize that the linear number system is what was what we sought was the numbers. Euclid was not dealing with numbers at all. So it's a remarkable fact that was proved in the 20th century that the line contains all numbers, until the complex plane was developed, which was in the 19th century. We'll circle back to that. So we have the plane, we have the Euclidean point, which is null because it's the center of the line. So we do have 0, but only in association with the line. What we're going to do is we're going to take Euclid's point, which ends up being 0 if you go to linear systematic space. That null point that is a geometric object with no linear dimension, that ends up being the number 0. And we all know that, but it's funny to say these things out loud. So there's our point. We also know that there's one infinity, the edge, where the diameter, you just say that it hits 2 infinities, but you don't say what that means because we don't know what infinity means. Yes, we do. We have a perfect descriptor for what is infinity. Can you guess? Just give it an adjective. What's the characteristic of infinity that makes it unique in geometry? It's imaginary. It's imaginary, but it's a very strange paradoxical thing to try to present to your own mind because we know it's there. Well, you have to say it's imaginary. You know why? Because we don't know where it ends. So if you're going to say that it's something, it would have to be something that has a limit. There is none. And so it's an imaginary limit. So that is a sphere that is unbounded. It's an unbounded sphere, and that's not a geometric object. It is, however, a geometric form. I was able to prove that the infinite line, it's bipolar infinite, is a subspace of that sphere. It's easily proved. You can prove it to yourself, but we're not going to pause because we're already at 52 minutes. What we want is to divorce that point from the line. We would now want to discard the line, and so we do. But now we're left with 2 things that we did not have without having begun with a line. But since we did begin with a line, we get 2 things, and then we don't need the line. But the line is there. That's extremely important. Another reason why nobody saw this is because you do have to embed the line in whatever higher space you want to develop, such as non-Euclidean space, because you need the computable numbers, and those are all on the line. So we just got computability into the unbounded spherical space. Now we need to bound it, otherwise we can't measure anything. And I'll show you why that's true. But first I just want to take this step by step so there is no slippage, so you see the exact proof sequence. We now have a point that has no characteristics. You could say that that 0, or I should say that null point, inherits the Euclidean characteristic, which is that it has no dimensionality. We're just going to say, sure, it actually doesn't make any difference. Although there's a footnote to that, it might make a difference. But what we're going to say is that it is the Euclidean point, plain and simple. But that's the only Euclidean object in the system. The edge is an unbounded sphere, which really has no definition at all. But it is there. We're saying so. This is my axiomatic basis. If you say that that line hits 1 infinity, then it's a spherical infinity. That can be proved. And therefore that spherical infinity has a center that's the same center as the line. So the point exists and the edge exists. They're both imaginary. Because now the point has no context. It's not a Euclidean point because the only reason Euclid invented the point to have no dimension is explicitly so he could make the line out of points. Because according to the way he thought this, and it's stood the test of time, to make the line the way it needs to be made so it will be useful, it has to be null. And that is imaginary. There is no such point. I did say that it does have a definition that you can attach to it that does maintain coherence. You can say later that it is a position in space. In this case, we're saying the same thing, but we're not defining the space as 1D, because that's the next step in the Euclidean sequence. It's sentence 2 of elements. The first sentence is start with a null point, and the second step we discard as being superpositionally incorrect. It does work, but we don't want to start that way. We want a different metricization of space. We don't want it linearized. We don't want lines in it. But we have to maintain computability. I just proved to you all the numbers are there. They're on the radius of that sphere. You could also say the diameter, but that's incorrect actually. It's the radius. Because it's the same distance from the origin, which is the null point. We're saying it's the Euclidean null. It's merely a position. But now it's not a position with respect to the line, because we're not using the line. We're using what the line gave us. But that 0 can be reparameterized so that it's not linear. It's not polar. It's not based on plus minus. What will it be based on? Because we do want a metric. Look at this. This is polar. Is there anything else? Yes, there is. There's this. And those are the only two geometric angles in basic mathematics and geometry. There's polar opposite, making plus and minus, that's add. But there's also this radius that goes out spherically, and that's one line. It's a straight line, but it's all the straight lines. That's called a pressure. A moment's thought will convince you of that. So there is a straight line, but it's not a Euclidean line. It's an integral line that comes from the origin and goes to the surface. How far is that? Infinity. So we haven't come too far yet. We still have an unbounded sphere, which means we can't use it unless we do something. So now I'm going to show you how to take care of spheric spatial infinity. It's by observing that it has a center. So the word that I wanted to teach you that's so magnificently important is the Archimedean. The Archimedean. That refers to a number space. Archimedean refers to a fulcrum point. It refers to a balance point. The Archimedean is always a point. At least it always has been a point. And Archimedes used this principle of balance in a geometric formulation to execute the very first calculus solution. Archimedes discovered the calculus. He discovered geometric calculus. He couldn't develop it very far. He wasn't as methodical as later was Leibniz and Newton. But he did use calculus to solve for the area under a parabola, which was quite a monumental feat because that's a curved line. The Greeks gave up on curved lines, although they did deal with a sphere and cylinder to figure out their approximation of the volumetric space of those closed objects. We're going to do way better than the Greeks. So we start with a point that is not a Euclidean point. Now, you know, I'm contradicting myself here. I keep saying it's not and it is, and it's not and it is. It's because it's both. And that's superposition. It depends on which system you're using, but you see the line is embedded in the sphere. So you can use either one. So it is both. And it's very similar to the quantum paradox. In trying to say, well, is it both? Or is it neither? Or is it either one? What's the deal? It's superpositional. It's either one. That's correct. It's either one. Can it be both at the same time? Well, let's offload that for the second because it won't affect our axiomatization. So now we need numbers. We don't have any numbers. In the unbounded sphere, there are no numbers. Now we have made a statement. We made a symbol, and we're going to call it lazy 8. That's spherical spatial infinity. The outside of the unbounded sphere, which is already a kind of a conundrum, a paradox is what that's called. We can now assign a number to it. You know how? You already know now that you can do that. You can assign an actual number, although it's a special kind of number, it ends up being a number. So how do we do that? We have a center, and we have an edge, and we know that there's such a thing as two-componency in multiplicative space. Because any pair of numbers that are reciprocal are 1. So those two numbers represent 1. What we're going to do now is derive the metric of spherical space by a very simple and absolutely watertight axiomatization. An axiomatization means that you're basically saying something that you cannot prove until later. So everyone's going to be on the edge of their seat if they trust you. Or there are going to be a lot of stern faces if they don't trust you, like, oh, sure you can. Let's see if we can do it. We know that fractions can be constructed so that they're 1, so that the two numbers are 1. That is, the two component numbers make one number. That's quite a mouthful, and if you stumble at that, I totally sympathize, but let me go through that again. The only numbers that are computable are linear numbers, but you can make fractions out of linear numbers that are computable. 1/2 is a representable and computable number on a computer. So is 2 over 1. So those two numbers, if you put them inside brackets, as you do with a complex number, that complex number with two components represents a number, not two numbers. It represents one number, but in conjugal space. We're going to do the same thing as was done with complex numbers, only it's much, much simpler, because it's based on the multiplicative identity. That these two numbers that are reciprocal, such as 1 over 2, and then you just reverse the numbers. 1 over 2 and 2 over 1. You put a comma between them and close it in braces. That is the number 1 written in two-componency form. That's a two-component 1. It's quite interesting, isn't it? It's not polar, because let's see what happens if we try to make numbers this way. We'll have to use infinity, so let's say that it's infinity over 1. You see, that's quite an interesting trick. Even though infinity is imaginary, you can pretend that it's a number until you prove that it has validity. Nobody ever saw this. I'm the first man to ever realize this can be done. It's miraculous what happens when you do it. Let's continue. Well, if the edge now is infinity over 1, we can say, and this is another axiomatic statement, that's larger than any other number. We're just going to say so. It's larger than any counting number, and therefore it's imaginary. But we're saying that it is a number. That's quite tricky, but it works, and I'll show you. So that's a number. Infinity over 1. That's a number. Is it imaginary? It certainly is. However, it's an imaginary number proportional to 1. So the goal here is going to figure out what is 1. I'll show you that it is the Archimedean. Of linear space, that's 0, of course, because it's the additive identity. This 1 is the multiplicative identity. So we're at least justified in assuming, just as a hypothesis, see where this goes. That number, infinity over 1, is a multiplicative number, except it's not multiplication. It's division, right? Well, those are two reciprocal operators. The multiplication takes two numbers and multiplies them. We think of that as repeated addition. There's a much better way of looking at it. It's taking the two numbers to 2D. So when you add, you stay on the line. But when you multiply, you make a rectangle. That's a fact. So that's the nature of multiplication. It changes dimensionality. Okay? But what if you invert that? What if you use division on your rectangle? Well, if it's 2 by 3, x2, and y3, that makes an area of 6. Well, you can then divide it by 3 and get the 2 back. Or you could divide it by 2 and get the 3 back. The question is, which is x and which is y? So it's non-commutative. And we were taught incorrectly that multiplication is commutative because you didn't say enough, because it's superpositional. They're mathematically commutative because you get the same number. I say you don't, but that could be debated. What cannot be debated is those two shapes are not alike. If it's 3 on the y-axis, it stands tall, and it's a little narrower than it is tall. But if it's 3 times 2, and your convention is x comes first, then it's lying flatter. It's 2 high and 3 wide. Well, those are not the same thing. So multiplication is mathematically commutative because you appear to get the same number, although even I'll show you that's actually incorrect. You don't get the same number because the number is oriented differently. But when you use division, you're simply undoing the multiplication. Correct? So they are inverse. Just as add and subtract are inverse. Subtraction, despite what I said, is a perfectly legitimate operation. All I said is that you don't need it. Well, you also don't need multiplication. But you do need proportionality, which we call division. So addition is the only operator that you need on the line. You don't need subtraction. And in fact, we're going to find out there are no negative numbers. That's really important, that the universe has no negative anything. But that needs to be proved. We will. But for now, we're just axiomatizing. You can say anything you want in the axiomatic sequence, but then you have to prove it. Otherwise, you're wrong. You're wrong if you can't prove it. So you have to prove it. Well, okay, that's really science. That's what it is. So, we now have a number, but it's a peculiar number. It's an imaginary number. Infinity over 1. That is spheric infinity. It's not linear infinity. It's not like these two plus minus infinity. This is outer infinity. Okay? So there has to be a reciprocal number, or that number is incomplete. Right? This is a hypothesis, so let's try it. Well, what's the inverse of infinity over 1? It's 1 over infinity. We're going to say that that's the center point. That that's its value. It's not 0, but it is imaginary. So is 0. 0 is imaginary. Well, 1 over infinity is also imaginary, but it's not 0. It's a multiplicative number. We keep saying multiplication because that's how we learned it, but it's incorrect to think of multiplication. We're not going to ever use multiplication. Unless we have to later. It does exist. But the way the universe is constructed is neither with subtraction, nor with negative numbers, nor with multiplication. It's with proportionality. And we call that division, and that's wrong to do that, although it's superpositional. Because in linear space, that would be division. But we're not constructing linear space, so it's not division. It's not division. There's no dividing of anything. It's the relationship between two quantities, and that's all it is. The outer number is the relationship between spherical infinity on the outside and unity, you could say, on the inside. We are saying that. It's the relationship of infinity to unity, and it's non-commutative because it It's invertible. So now we say that because the edge is infinity over 1, therefore the Archimedean is 1 over infinity. That will turn out to be incorrect. So we're not going to say it's the Archimedean, because I know that it's not. But we're now going to get the Archimedean. Which, what would that be? What would that be for this space? Because there's only one other Archimedean besides 0. It's 1. So that's what these two numbers multiply to. The center is 1 over infinity, defined as a number so small that it's imaginary. It's smaller than any number. Technically, all you have to say is it's smaller than 1. It's less than 1, but it's not 0. But you see, it also has infinity in it. It's just that infinity is on the bottom now, and 1 is on the top. So that makes an infinitesimal. That's technically an infinitesimal. I will now show you that that is the only infinitesimal in physical space. There's an infinite number, actually an infinity of infinities, of irrational numbers, which are infinitesimal numbers, on the line. But in the space we're constructing, there will only be one infinitesimal. The center of the system at this moment is that imaginary point. It's critical that you realize that's imaginary. Okay? And now we're going to go forward. So now we have two numbers that multiply to 1. Infinity over 1 and 1 over infinity multiply to 1. That everyone knows. There's no doubt about that. Now the question of what's happening to the infinities will be solved at the end of our proof, and will obtain closure and completeness. Actually, violating Kurt Gödel's incompleteness theorem, in context, it's the first violation discovered. I discovered the first violation of Kurt Gödel's incompleteness theorem, because we defy Kurt Gödel's incompleteness theorem by going inside out. And that gets rid of that paradox. And it is a paradox, what he came up with. Although it's profound, it's a paradox. Now we have two numbers, a center and an edge, right? Visualize that. There's a point. In fact, let's take a quick look at this again. Oh, look, there it is. So there's the center point is that bright light. And the edge is some edge. You could say it's the edge of the pink section, but then there's something going outside of it. Or you could say it's the edge of the plumes. That doesn't make sense since they're still expanding. So we're talking about the edge of the universe. The edge of the universe, which is imaginary. Well, that means that the center is also imaginary, but it makes infinitely bounded space. That's a contradiction, isn't it? You'll see that it's not. It's superpositional, but this is the solution to superpositionality itself. We now have infinite bounded space, and there is no zero. There is no zero. Although you can see that that point might be 0. I'll prove to you that it is, but superpositionally, so that you can have both. It's very important, this duality, that you have to correlate your object with the space in which it's embedded. Euclid never realized that when he drew that line, it's embedded in spherical space. It wasn't until 2022 that that simple fact was noticed. I got it. But then nobody could take the second step, because surely other men realized that. But they didn't know what to do with infinity. There's actually several more paradoxes that have to be solved. For instance, how to keep the linear numbers, which are the only computable numbers, in a space that has no line. This space does have a line. It's just we don't use it. It's there, we just don't use it. It's a derivative space of spherical space that has an exact solution. And that also needs to be proved. Now we're getting up on 100 minutes. So this will go to a third lecture, but I do want to achieve closure here so you'll have something to take away from this that's of inestimable value. So you multiply the two numbers. What is 1 over infinity? You could say it's infinitely small. So it is less than 1 because it's infinitely small. So it's definitely less than 1. Well, infinity over 1 at the edge is so large that it's imaginary, so it's definitely greater than 1. So now we have a relationship between the center and the edge. Numbers. The center number is infinitesimal, and the number at the edge is infinite. And that bounds space spherically. But it bounds it with an imaginary boundary. So we're still not done. Well, all we have to do is multiply the two numbers. What do they multiply to? They multiply to 1. Well, draw it. Where's that 1? It has to be between the center and the edge. Because the number that's less than 1 has to be inside. And the number that's greater than 1 has to be outside. Well, the number that's greater than 1 is infinitely far away from the center. It's also infinitely far away from 1. The center is infinitely smaller than 1. Right? But where's the 1? It's a sphere that's in between the center and the edge. It's much smaller than the edge of the universe. It's the quantum of spherical space. So now we have a third number that's not imaginary, and that's the Archimedean of spherical space. It's a surface, and that's called intrinsic geometry. The geometry of the spherical surface will give us the solution that unlocks space-time and solves the quantum paradox and solves all the astrophysical problems having to do with the singularity. So revolutionize science. Thank you for tuning in. This is Anagalactic bringing you the secrets of the universe. I need to refresh myself with water, and I need some food. I need a lot of things, some medicine. But we'll be back later today. It's currently only 5 p.m. here. I expect that I'll have enough energy to complete a third video to complete our series today. So you get the answer to what is a BH. What is an SMBH? What is a panther? What is a quasar? What is a galaxy? We can't go so far as to say what is the universe, except to state one thing. It's definitely not a Big Bang. That's completely out of the question. That was just a placeholder until we could grow up a little, and I'm very happy and humbly proud before my God that He let me see this, and I pray that I'm not deceiving anybody, but in my own mind it's not possible that this is a deception. This gets it all. So stay tuned. This is Anagalactic. Keep looking up. We'll be right back.